Hello, we have two chapters left in the block, and they're both dealing with the properties of large systems. So we've learned about molecules and bonding and what properties individual molecules have. Now we're going to talk about what does a system of gas molecules, or what does a solid look like, or what does a liquid look like in reference to what we know about the molecules. So we're going to start with gases. And this is chapter 9 in your book, but chapter 10 in this newer edition. So everything is exactly the same as chapter 9. So gases. Gases are homogeneous and compressible. So another way to define a gas is to say that it's a system that moves to occupy the entire volume. So it's a large collection of particles moving at random through a volume that's primarily empty space. And the collision of randomly moving particles with the walls of the container exert a force per unit area that we perceive as the gas pressure. So force per unit area, F over A, is our definition of pressure, and that will be an important property of gas systems. So force per unit area, the unit area is just whatever container. So if you're thinking about this gas in this container, you could think of the area of the inside of the container creating the pressure. Or you can think about another way to think about pressure would be the force per unit area, for example, from gravity. And so the force of gravity is mass times the acceleration constant. And if we were talking about some area on surface Earth, what the pressure would be, it could be any surface area that we want to look at. Here they're looking at a meter squared for the area. So if we have a mass of 10,300 kilograms and we're talking about a unit area of a meter squared, we multiply the numerator by the acceleration due to gravity, you'd end up with a pressure of 101,000 pascals. So if you're dealing with SI units, you're going to end up with pascals as your pressure unit. So we know, I mean, if you have a system of gases, it's going to be at a temperature, some volume, some number of moles, and some pressure. And we know how to measure volume and temperature, but we really haven't talked about how you would measure pressure. So if you want to measure atmospheric pressure, you're going to use something called a barometer. And so you have a column of mercury sitting inside a mercury dish, and there'll be pressure both on the surface of the dish and then also up above in that column where you have the empty space. So the empty space above the mercury in the sealed end is a vacuum, so that means that there should be no pressure. And the downward pressure of mercury in the column is exactly balanced by the outside atmospheric pressure that presses down on the mercury in the dish. So we know that in the column, that mercury has a pressure due to gravity. And so how high that column is will be a different pressure. And so when atmospheric pressure is pushing on the bowl, it can push the column up against gravity if it has more pressure than the gravitational pressure pushing down, or vice versa. So you can use this system to measure pressure, atmospheric pressure, by measuring how high the column is. The units of pressure are Pascal if you're in SI units. A torr is equivalent to a millimeter of mercury, so the second and third one are the same. Millimeter of mercury just comes from the idea that the millimeter of mercury in this column is proportional to pressure. Atmosphere is another pressure unit, and bar is another pressure unit. Your book has, well, they're right here. So here are the conversion factors. So if you're working with a barometer and have some millimeters of mercury in the column, you can convert it into atmospheres by knowing that 760 millimeters of mercury is an atmosphere. 1 torr equals 1 millimeter of mercury. 1 bar is 10,000 pascals, and 1 atmosphere is 101,325 pascals. So you have that table in your book, and you are free to put that on the your note card if you want to. we want to measure the pressure of a gas rather than measure atmospheric pressure. Here you have a manometer rather than a barometer. And so if we look at the gas in this bulb and we're comparing it to the pressure of atmosphere, if you have a pressure of the atmosphere pushing on one side of the column, the pressure of the gas on the other side, if it was exactly the same as the atmospheric pressure, then there'd be no difference in the height of the two columns. But if the atmosphere is pressing harder than the gas is, so that there's a greater pressure outside the gas bulb rather than in, then the side towards the gas will be higher because the atmospheric pressure pushes it further. And then vice versa. If the gas has a higher pressure, the system on the right-hand side, so the pressure of the gas is greater than an atmosphere, then the column of mercury will be higher on the side of the system open to the atmosphere. So the physical properties of a gas can be defined by these variables. So as I mentioned, we already knew about temperature, volume, and number of moles, but now we have some idea of how you would also measure pressure, and those are all important physical properties you need to know to understand what state a gas is in. So the gas laws were developed by individual experiments, not an experiment where you related all of these. But Boyle started out by holding number of moles and temperature constant and just looking at how volume and pressure changed. And what he discovered is that they were inversely proportional. So as volume went up, pressure went down, and vice versa. So that was one set of experiments. That would mean that if you graph volume versus 1 over pressure, you should get a straight line. And if you graph just volume versus pressure, you'll get a hyperbola. So you tend to want to set up equations so that you're graphing things that are linear. It's easier to see. So this graph on the right-hand side, if you do 1 over p instead of p, makes the equation into a straight line. So Boyle's law says that volume is proportional to 1 over p. That's the same thing as saying p times v equals some constant. So if you take the p over to the left-hand side, that's the same thing as saying that it's equal to a constant, and k is essentially the proportionality constant. Also means that if you hold number of moles and temperature constant in your gas, that pressure initial times pressure, or volume initial, is going to have to equal pressure final times volume final. So if all you do is change the pressure and volume, you'll be able to know how they change relative to each other by knowing that their product has to be constant. Charles' law is another set of experiments where now we're holding pressure and number of moles constant and looking at how volume changes with temperature. And what you see is that if that's what you do, so you add some heat so that the temperature goes up, the volume is proportional to the temperature. So volume goes up, temperature goes up. And so that means that if you plot volume versus temperature, you should get a straight line. And it's going to make more sense, and we're going to try hard to always know that it's best to work in Kelvin when you're dealing with with gases. Just we'll see why in a little while, but one graph here is graph degrees Celsius, one is Kelvin, and the graphs are fine, but we'll see that it's going to be a lot, it's going to make a lot more sense to always do things in Kelvin. So Charles' law, you can think of it as we did with Boyle's law. If volume is proportional to temperature, that means volume over temperature equals a constant. If volume over temperature equals a constant, when you hold moles and pressure constant, then that means volume initial over temperature initial has to be equal to volume final over temperature final. Avogadro's law looks at experiments where you're holding temperature and pressure constant, but you're just adding more gas or taking gas out of the system. So you're looking at how volume depends on the number of moles of gas particles you have. So at constant temperature and pressure, the volume of an ideal gas changes proportionally with its molar amount. And so if the molar amount doubles, the volume doubles. So they're directly proportional to each other. And so just like the other laws, you can rearrange them to think of how this could be useful. So if volume is proportional to the number of moles, then volume over number of moles is equal to some constant. So that constant will always be the same if T and pressures are, temperature and pressure are the same. That means the volume initial over the initial number of moles, if you're holding temperature and pressure constant, has to be equal to the volume final over the final number of moles. So here's just a summary of those, and we're going to put these all into an equation that we'll call, that'll be combining all of these in a second. So molar volumes of some real gases at 0 degrees and 1 atmosphere. Notice that they're all almost exactly the same. So what we'll discover is that the properties of gases are really independent of what type of molecules we have. So each of these is about 22 units, 22 liters for a mole of each of these gases when they're all at the same temperature and pressure, 0 degrees Celsius and 1 atm. So we can take all of those laws and we can pull them together and we end up with the ideal gas law. So once again, noting that pressure and volume are inversely proportional. Volume is proportional to temperature and number of moles. So if you combine Avogadro's law, Charles' law, and Boyle's law, you can get the ideal gas law. So the ideal gas law is an approximation, but it's a pretty darn good approximation for most gases, even gases at 1 atmosphere and room temperature. They pretty much follow this ideal gas law. So R is the gas constant. It's the same for all gases. And what you notice immediately in the ideal gas law supports what we saw here in experiment, that no place do you have to tell the equation what gas you have. You have to say how many molecules I have, because you have number of moles. You have a gas constant, which is the same for all gases. You have the temperature, the volume, and the pressure. So it's an equation that supports what was seen experimentally, which is that pressure, volume, and temperature are related in the same way, independent of what gas you have. The standard temperature and pressure, I don't like to use that terminology. So I'll always tell you the gas is at 0 degrees and 1 atmosphere versus calling that STP, simply because in our chapter on thermochem, our standard temperature was 25, so it gets a little bit confusing why for gases you change it. So rather than saying a gas at STP, do some calculation, I will say a gas at 0 degrees Celsius and 1 atm. So here is that graph again, showing you that these are all about the same. The molar volume of all these gases are about the same at the same temperature and pressure. And so what's the volume of 1 mole of gas at STP? So at 0 degrees Celsius and 1 atm. So we're going to look at our table that gives us different gas constants. There's one that's in liter atmospheres in the numerator and Kelvin times moles in the denominator. We'll see that'll be the one that will work to give us a volume unit. So volume, if we rearrange PV equals nRT, we just take P over to the right-hand side. So you end up with volume equals number of moles times the gas constant times temperature divided by P. We have a mole, that was the question. The gas constant in liter atmosphere is K mole. Temperature in Kelvin, 0 degrees Celsius is 273.15 Kelvin. And our standard pressure is 1 atm. So if you look at everything in that equation, the moles cancel, the kelvins cancel, and the atmospheres cancel, and you end up with 22.41 liters, which is very, very similar to these experimentally measured molar volumes for gases. So we saw a lot in chapter 3, different ways to essentially mix quantities or to understand how much you're mixing. So if you're carrying out a reaction, you might take different masses and then figure out how many moles you had. You might also have some solutions that you've dissolved some of your reactants into liquids, and then you take different volumes. Here we're going to think about gases and think about taking different volumes, but knowing that with gases, rather than using molarity, we're going to use the ideal gas law to figure out how many moles we have. One of my cats is just going crazy, running back and forth. The reaction used in the deployment of automobile airbags is the high temperature decomposition of sodium azide, so NaN3, and it produces N2 gas, which then creates the huge volume that protects you from hitting your steering wheel or your dashboard. So how many liters of N2 at 1.15 atmospheres and 30 degrees C are produced by decomposition of 45.0 grams of sodium azide? So you can't use the ideal gas law for the sodium azide, but we can use it for the nitrogen. So when we start out 45.0 grams of the reactant, we're going to have to convert that to moles with the molar mass. So that's where we'll start. So 45.0 grams of sodium azide. The molar mass of sodium azide is 65.0. So 1 mole is 65.0 grams. And when we look at the stoichiometry, you get 3 moles of nitrogen for every 2 moles of sodium azide. And so we end up, same type of calculation as chapter 3 with 1.04 moles of nitrogen. But if we want to think about what volume that is, we can use the ideal gas law because it's a gas. So we'll use the ideal gas law rearranged with the pressure on the right-hand side. So 1.04 moles. Once again, the gas constant in liter atmospheres per K mole is the appropriate set of units here because everything will cancel except the volume. Kelvin for the temperature. Yeah, it's set at 30 degrees Celsius. So you add 30 to 273, so 303.2 Kelvin. And the pressure given was 1.15 atmospheres. And so you end up with 22.5 liters. So you start out with a little bit of a solid and you get a large volume, which can fill that airbag and protect you from hitting your head. So maybe, yeah, I think I'll take a break here. We don't have a lot left, but I might as well take a break and do it in 2 sections. It's a little bit easier for you to force yourself to take a break and kind of let that all sink in.